I have 4 conference papers in this session. The first paper is Virtual versus Physical Navigation in VR, Study of Gaze and Body Segments, Temporal Reorientation Behavior by Hugo Brument, Iana Podkosova, Hans Kaufmann, Anne-Hélène Olivier, and Ferran Argelaguet Sanz, and Hugo is going to give the talk.
Okay. Thank you for the introduction. So, good afternoon, everyone. My name is Hugo Brument, and I'm from the University of Rennes. And we did this work in collaboration with the Technische Universität of Wien. So this talk is about how gaze behave and how our body segments, meaning the head and the shoulders, behave during a navigation task. So first, we did this work because our motivation was to understand better the human behavior during a navigation task in virtual environments. And we focused our study on gaze anticipation. So in real environment, it has been demonstrated that if I'm walking in this straight line and I want to walk towards the audience first, my gaze will anticipate the future trajectories. My gaze followed by the head and the shoulders, the body segments. And this reorientation strategy follows a top-down reorientation. So when I will use gaze anticipation, that would be the anticipation of the gaze, and the top-down reorientation means that the gaze anticipates then the head and the shoulders. So our question is, this has been proven in real environments, but what about in virtual environments? Do we also have a gaze anticipation when we are walking with the HMD? And do we also have this anticipation if we are using virtual travel techniques such as steering with a joystick? So in real environment, various studies proved this anticipation, as I said, and for different trajectories, such as 90 degrees trajectories, 30 or 60 degrees trajectories, or complex curve trajectories, such as a lemniscate. But as I said, we have not a lot of data about and results about in virtual environments. So the few studies that has been done assess the gaze behavior for 90-degree turns with passive motion or walking in place techniques. Other studies try to predict trajectories along a corridor to detect whether the user would turn to the left or to the right. So based on this related work, our research questions are gaze anticipation and top-down reorientation preserved during navigation in VR? And is there an effect on the navigation techniques on this anticipation and the top-down reorientation? So our experiment assessed and analyzed gaze behavior and body segments reorientation strategies during navigation in VR. As I mentioned about the related work, most studies focus on 90 degrees turn. So we were inspired from previous studies done in real environments, and we analyzed the gaze behavior during curved trajectories, such as this lemniscate trajectory, the H shape. We used several navigation techniques, and our baselines were to compare physical techniques, such as walking, with virtual techniques, such as steering, spatial steering techniques. And so we designed a new control law to adapt the velocity, and this control law is based on the relation between the speed and the curvature. I don't have time to describe this control law, but you can find more detail on the paper. So regarding the navigation techniques, our baseline was to compare walking that requires physical travel with virtual techniques. And in order to choose the techniques we want to test, we focus on 3 criteria. The first one is the popularity, how often those techniques are used in VR application. The second one is the control that the techniques provide to the user. And the last one is the body segments orientation that controls the future direction. So we had 5 different navigation techniques, including walking, where the user walks in the virtual environment as he walks in the real environment. 3 steering techniques, torso steering, hand steering, head steering, where in torso steering, the torso orientation defines the future direction. In hand steering, this is the user hands that defines the future direction, and in head steering, that's the head that defines the future direction. And the last one is passive navigation, where the motion is fully automated. It means that user's viewpoint in the virtual environment is automatically updated. With these techniques, participants had to perform the following experimental task. So this is the walking condition. So the user starts at the center of the virtual environment, and he has to perform the lemniscate shapes. So he will do the first turn and then the second, and he will go back at the center of the virtual environment when he started, and that will validate the trajectory. So during this experiment, they had to perform 10 times this trajectory. In steering conditions, for this one, for example, this is hand steering, the Vive controller's orientation defines the future direction, and the user is able to perform the virtual lemniscate trajectory with these steering techniques. So this is the same requirements. The user has to end his trajectory where he started, at the center of the virtual environment. So for this experiment, we have 20 participants without any ocular or locomotor disorders because it can impact the anticipations. And for each participant, we recorded the following data, especially about body segments and the motion. So thanks to the eye tracker, including the 4HMD, we were able to have the left and right as the gaze position and orientation. Then we recorded head position and shoulders position and orientation thanks to 3 Vive trackers attached to the user. We also computed some subjective measures, such as simulator sickness scores between each conditions, NASA TLX test to assess users' mental demand, performance, effort, and frustration. And we also, user subjective preference about the techniques were considered at the end of the experiment. So these collected data were analyzed, and we mostly analyzed the trajectories, meaning the mean curvature, the time to perform the task, and the distance achieved in real and virtual environments. We also compute the navigation speed to see how fast they were navigating. To assess body segments' temporal orientation, we analyzed horizontal angle of body segments. So how is the orientation of my body segments, the gaze, the head, or the shoulders when I'm performing the task? And to compare this anticipation, we computed cross-correlation between those body segments, because a cross-correlation describes the delay between correlated signals, and they show the lag between the temporal sequence. So before starting this experiment, we had 3 different hypotheses. First one is users perform the trajectory in a similar manner with the different navigation techniques. So we wonder if the user would perform the H shape, the lemniscate shape, with same curvature and speed. Then we had H2. Gaze anticipation is preserved during navigation in virtual environment for the walking condition. It means that we wonder if the navigation technique, it means that we wonder if the gaze would anticipate the future trajectory as it was shown in real environment. And the last one is top-down reorientation strategies differ depending on the navigation techniques. We wonder if the navigation techniques could have an effect on body segments orientation. So H1 was validated, and you can find the details in the paper if you want. And now we will only focus on H2 and H3 for the anticipation mechanism. So regarding H2, we wanted to check the gaze anticipation with the HMD. And here is a figure when you have the temporal evolution of the body segments, the angle that I described before, during the time. And what we can see is that we have the gaze in green and the head in orange, and there is this left shift with respect to the heading direction. And this left shift shows the anticipation of gaze and head with respect to the heading. It means that my gaze and my head turns before and anticipate the future trajectory. And the cross-correlation showed that the gaze anticipates the trajectory followed by the head with respect to the heading direction. So this validated our hypothesis H2. Regarding H3, we wanted to see if there are some differences between gaze anticipation during walking and the other virtual techniques that I described. And the main result is that virtual techniques generate different anticipation mechanisms than walking. Here you have on the y-axis the temporal anticipation, the cross-correlation results, so the anticipation of the gaze in gray and the head in blue, for each technique, so walking, torso, hand, head steering, and the passive. And here are the results of the gaze anticipation for the walking condition in real environment for the gaze and the head. And we can see that the anticipation of gaze and head is higher for the walking condition in virtual environment than in real environment. Besides, the post-hoc comparison showed that there is a higher anticipation of gaze and head in walking and torso steering than the three others virtual condition, that is hand steering, head steering, and passive. So walking in virtual environment or using torso steering to define the future direction induced significantly larger gaze and head anticipation on the trajectory. Besides, we can also notice a high variability for the hand steering and the passive techniques, where the user had some issues to anticipate or not the future direction. So from these results, we noticed the several interesting points. The first one is that the higher gaze anticipation in virtual environment for the walking conditions. And our hypothesis is that they may be an effect of the field of view on the anticipation. Since we are wearing HMD, we have a restricted field of view, so maybe the user has to anticipate more the future direction than in a real environment. Torso steering has the closest behavior than walking compared to the other virtual techniques. And this result can be explained by the fact that in real environment, some studies shows that the torso can be compared as a steering wheel that define the future direction. So the torso is a good reference frame to define the future direction when we are navigating. Head steering, even though that's a popular technique, it doesn't allow gaze anticipation. Since the head is defining the future direction, I can't anticipate the future direction because the head is defining this one. And one of the most interesting things that we can discuss is that we had 5 users with the head-shoulders delay lower than 50 milliseconds. It means that they are turning the head and the shoulders in the same time, and it results in what we call en bloc strategy. So it's like the head and the shoulders moves into one block. And this result has been already noticed in real environments for humans having a stroke or physical deficiency. And so we could discuss and argue about that body segments anticipation could be a new metric to assess the navigation techniques. And last, as I said in the results of the previous slide, high variability about the passive navigation when the user viewpoint is fully automated, so we don't know sometimes how to anticipate because we don't control the viewpoint update in the virtual environment. So some users were able to move and to anticipate, and some were not able. So as a conclusion, the contribution of this study is the assessment of gaze behavior in virtual environment with different navigation techniques. And these results help to understand better the human body segment's behavior in virtual environment. So our objective is to improve navigation in VR, and we believe that interaction techniques based on human locomotion laws could improve the user navigation experience. And as future works, as I see, there is no real walking condition, and so we have to assess the impact of field of view and the effect of field of view in VR by having this real condition. And we have also to conduct another experiment in a more ecological task, because we needed to have no silent point and feature to assess the anticipation mechanism. Thank you for your attention, and if you have questions, we'll be glad.
So we have time for questions. If you can step up to the microphone, and if you can state your name and affiliation.
Hi, Jean-Rémy Chardonnay from Arts et Métiers in France. I have 2 questions actually. One that, so you test with a head-mounted display, but did you consider also visualization devices, like a cave or, because I know that in Rennes you have a very large cave, so probably you could have tested the same. And the second question is regarding the speed, navigation speed. Did you find some differences between real walking and the different techniques?
Okay, so yes, I will first answer about the cave. We consider that it could be a condition, but it was already a huge protocol, and a good experiment. So we didn't want to compare directly between cave and HMD. So we only focus on the HMD. We wanted to see the anticipation on the HMD. But of course, we can conduct an experiment and to compare and assess in a cave environment. For the mean navigation, there are no effects because we designed the controller in an empirical way so that we will have similar walking profiles, speed profiles in the walking condition and the virtual condition. So to assess the controller, we just make some user walking and we adapt the parameters of the controller that you can find on the paper so that it matches and we have similar walking speed so that it won't bias the results of the cross correlation.
Okay, thank you. Nice talk.
So we have time for just one quick question.
Okay, nice talk. I'm Lily Wang from Beihang University, China, and I'd like to know if any, I think the gaze and the locomotion related to the content of the scene and maybe the task. Did you try the more complex things and with some maybe searching task? Is the same result for this?
Okay, thank you for the question. So yeah, actually that's an interesting point and I haven't detailed it that much. But what we wanted to, so in real environment, the task and the context of the environment influence our gaze. So what we designed, and that's why the environment is very simple without any assigned point features, because it could bias where the gaze would look. So that's why we remove any visual information in the virtual environment so that the user can't be attracted, the gaze can't be attracted by any kind of virtual object in the scene. But yes, we should consider in a more ecological task, as I said at the end, with other navigation tasks.
Okay, right. Thank you.
Thank you. Let's thank the speaker again.